Okay, ladies and gentlemen, so let's get straight into today's chemistry lesson. So, today's chemistry lesson, we're going to continue our discussion on the periodic table, but more specifically, we're going to begin to focus on um, electron configuration of the periodic table. So, let me go ahead and get this arranged and we can get started. So, the first thing worth noting about the electron configuration is that the elements in the periodic table are arranged vertically and horizontally. Um, Vertically by groups, horizontally by periods, and we're going to talk about that in just a minute. Um, so the first thing worth noting about the electron configuration is that the electron configuration of an atom's highest, the electron configuration of an atom's highest um, occupied energy level governs the atom's chemical properties. So, as we all know from our previous lesson, when Mendeleev started to develop the first periodic table, he wanted to arrange elements in a way that they were organized by similar chemical properties. Later on, as further studies were developed and Moseley arranged atoms by their atomic number, it was later concluded that the atoms have are arranged in or have an electron configuration which we did talk about in a couple of videos prior. And in a nutshell, what this is saying is that it's the electron configuration. It's the electron in the highest occupied energy orbital that determines the element's chemical property. So very important, worth noting that. Now let's talk a little bit about the period of an element in or how the period of an element, excuse me, is determined by its electron configuration. It says while the elements are arranged vertically in the periodic table in groups that share similar chemical properties. So again, elements are arranged in are arranged vertically, excuse me, are arranged vertically in the periodic table to show, excuse me, in the periodic table in groups that share similar in groups that share similar chemical properties. So the groups which are arranged vertically on a periodic table. So let me see if I can. In a minute, I'll illustrate that. But basically, the groups that are arranged vertically share similar chemical properties. But one thing worth noting is that they are organized. Is that they're also organized horizontally. Okay, they also organized horizontally. So here we go. They are also organized horizontally. They are also organized horizontally. and they're called rows or periods. So organized horizontally in rows or periods. And they're also organized horizontally in rows or periods. And the length of the period is determined by the number of electrons. So this is worth noting. The length of the period is determined by the number of electrons that can occupy the sublevels being filled. That can occupy the sublevels being filled. So, what I am trying to say is this: if you have a periodic table and they're arranged vertically, and this is more or less what most periodic tables can look like, depending on the textbook or just if you look for one off the internet, it kind of looks like this. So they're arranged vertically in groups. So, for example, this is group one, this would be group two, three, four, five, and all the way up to 18. And they're also, so the group is vertically, and elements that are arranged vertically have similar chemical properties, but they're also arranged horizontally. So I can have an element that is in group one, but can be in period one, in period six, all the way down here, just to to give you guys an idea. And the horizontal arrangement is called periods. Okay, let's see if I can fix that too a little bit. The horizontal arrangements are called periods. So group is vertical, periods are horizontal, and the period or the length of that period is determined by the number of electrons that can occupy the sublevel being filled. So, for example, if we look at period two, if we were to look at the second period of the table, the period two would start, let's say, with lithium, and it would end all the way with fluorine, for example. And the reason that is, uh, and if you look at it, the orbital that is being filled uh, is the S sublevel, and it goes all the way from 2s all the way up to 2p. So the length of that period basically determines, or basically the sublevels that's being filled is what determines the period. So if it's period two, that means that period two can fill S sublevels and P sublevels. So that means that the length of the period will go from S all the way up to P if we're talking about group two. And I know that can seem a little confusing, but we'll talk about that in just a minute. Just to kind of recap the points that I've written down so far. Number one is that the electron configuration of an atom, the electron configuration of an atom's highest occupied energy level governs the atom's chemical property. Secondly, that elements are arranged vertically in the periodic table in groups that share similar chemical properties. Next thing is that they are also organized horizontally in rows or periods, and that the length of the period is determined by the number of electrons that can occupy the sublevels being filled. So if we talk about group two, period two, generally the S and P sublevels are being filled, and it's going to last according to how many electrons are being filled. But let's go then. Let's talk about that real quick before I move on to anything else. And for example, before I move on to anything else, if there's a table in your textbooks, specifically in figure 2.1, where they give us the period numbers basically from 1 through 7. So let me go ahead and do that. So we know that there are 7 periods. That means that there are 18 groups, or elements are organized vertically into 18 groups and horizontally into 7 periods. So there are 7 periods, and we have 6, and we have 7. And for example, the number of elements in each period. So group 1, which is the shortest, so this is their number of elements. It's not a hashtag. And I'm just gonna to hurry up, I'll just write E. But you know what? I think I can do it something better. So let me just do this. So in this column, we'll say that it is the number of elements in the period. And then let's see if I can make this space smaller. And then the other column is the sublevels in order of filling. So let's look at each one. So the number of elements in period 1, to be specific, if I look at the first period, the number of elements in period 1 are just 2. So you only have 2 elements in period 1, which are generally hydrogen and helium. Okay, so basically you have 2 elements in period 1, which are hydrogen and helium. In period 2, you have 8 elements. So period 2 have 8 elements, which basically start at lithium and end all the way up in neon. So 8 elements. In period 3, you also have 8 elements, which start from sodium and all the way in argon. So basically, sodium and argon. Period 4, has 18 elements, as does period 5. And period 6 and 7 has 32 elements. But theoretically, in period 7, you can expand that to 32, but there are 32 elements in period 7. Now, the way the sublevels are filled is that we know that elements in period 1, hydrogen and helium to be specific, fill up. The sublevels that are filled are basically the 1s. Period 2, you fill the 2s, and the 2p sublevels, respectively. In period 3, 3s and 3p, and 3p. Give me 1 second here, guys. There you go. 3s and 3p. 4s, 3d, and 3p would be the fourth period elements. 4s, because remember that when we talked about that in other examples. Fifth elements are 5s, 4d, and 5p. 5s, 4d, and 4p, and 5p, excuse me. The sixth period are 6s, and these are, when we get to the sixth and seventh period, those electron configurations can be pretty tricky. So that's why in these introductory courses we really don't talk much about the electron configuration of those elements, due to, however, see them in other chemistry courses. 6s, 4f, 5d, and 6p. And then the seventh period elements are 7s, 5f, which is why noble gas notation is used a lot, especially with these fifth and sixth period, sixth and seventh, basically fifth and sixth period elements use a lot of noble gas notation because it is easier to organize the periodic table. So 7s, 5f, 6d, and 7p. And 7p. So basically that's the table, and that table just is pretty much giving an idea of how elements are organized. Now, it's worth noting that the period of an element can be determined from the element's electron configuration. So let me go ahead and erase this. If you have any questions, you can always pause the video and kind of look at what I just wrote, or you can make reference to this table, which is figure 2.1 of your textbooks. So let's continue on with the rest of the section for today. And write some general information down. You can always make reference to your textbooks. The sections or the pages that were discussed today are basically the beginning of section 5.2, which starts on page 130. So as I was mentioning, the period of an element can be determined by the element's electron configuration. For example, we have argon, or arsenic, excuse me. We have arsenic. or arsenic. And arsenic has an electron configuration of argon, argon 3d10, 4s2, and 4p3. 3d10, 4s2, and 4p3. It says, so basically, if you notice, the 4 in 4p3 indicates that arsenic's highest occupied level is the fourth energy level. So basically, if I were to look specifically at this, I know that the highest energy level occupied is 4. Okay. So by looking at the 4p3, I know that the highest occupied energy level is 4. So I know that if I look at the electron configuration and look at the end, I know that the highest energy level occupied in arsenic is 4. Okay. Again, the 4p basically indicates that arsenic's highest occupied energy level is the fourth energy level. So by knowing that, we can say that arsenic is a fourth period element. Okay, so that's basically what it's indicating, that arsenic is a fourth period element because the highest energy level that is filled is the fourth energy level. So another thing worth noting is that the name of each block in a periodic table is determined by what is determined by whether an S E D or F sublevel is being filled. Right. So if you make reference in your textbook, there's a periodic table, and basically there's a legend and it's divided by color, and it indicates which elements are the S elements, which elements are the P elements. So basically, group 1 and 2 are pretty much S blocks because the S sublevel is filled. The groups 13 through 18, excluding, of course, helium, are basically P block elements because the P sublevel is being filled. The on the table, it's color coded by yellow, and basically groups 3 through 12 are what we call the D block elements because, again, the D sublevel is being filled, and the F block elements are pretty much the elements that range from the atomic number 50, 58 through 70 through 103. and they're at the bottom of the periodic table. Interestingly, they're at the bottom not just because they're man-made, but also because it helps them organize them. Because technically, they would be falling into the groups um, 3 through 12, but they just do it that way because they're mainly man-made and just so that the periodic table looks a bit organized. But that's more of a side note. It's not really relevant to what we're discussing. Okay, so now that we understand, have a little bit more of a basic understanding of this, let's go ahead and talk about S block elements. Okay, so basically, S block elements. S block elements are usually reactive metals and are, again, like I said, are in group one and in group two. In group one and in group two, they have an electron configuration of ns1, of ns1 and ns2, excuse me, of ns1 and ns2. So let me see if I can basically have an electron configuration of ns1, which I'm writing here. And that just means that in the S sublevel is going to contain either one or two electrons. So basically, they have an electron configuration of ns1 or ns2. Sodium, which is actually a group two, excuse me, a group one element, has a third period. So basically, sodium is in the third period. If you look at your periodic table, remember horizontally, third period, and N N for ns1 or ns2, N indicates the period in which the element is located. So if we look at the periodic table, sodium specifically is in period 3 because it is in the third row. So the electron configuration for sodium is in group 3, period 3, excuse me, and we know that it is in group 1, so it has an electron configuration of ns. So I would say I would write it as 3 because 3 indicates the period, and I realize I did not finish writing the word period here, so period. So n equals period, so ns, n is the period, s is the sublevel, so obviously sodium is in the third period, so it'd be the s sublevel. And the exponent just indicates the S1 or S2, just indicates if it is in either group 1 or group 2. In the case of sodium, it is 3S1 because even though it is in the third period, as indicated by the 3, it fills the S sublevels, but it is in group 1. So that's why sodium has an electron configuration of NS1. Okay. Um, Group 1 is referred to as the alkyl earth metal. Group 1 is referred to as the alkyl earth metals. And the elements in group one are range from, excuse me, lithium all the way up to francium. From lithium to francium. So you have lithium, sodium, potassium, rubidium, cesium, and francium. Basically, from lithium are lithium, sodium, potassium, rubidium, cesium, and francium. And some of the characteristics of them is that um, in their pure state, they have a silvery appearance. Have a silvery appearance. Are soft and very reactive. Are soft enough to even be cut with a knife. Are soft, very reactive, and are not found in nature as free elements. They react with water to produce hydrogen gas. To produce hydrogen gas in aqueous solutions. Okay, so now let's talk real quick about the group two elements. Let me just erase some of these things over here so I can have some more space. Let's talk real quick about the group two elements. The group two elements and we're almost done here, guys. So the group two elements consist of beryllium, magnesium, magnesium, calcium, strontium, barium, and radon. Barium and radium. And the group configuration is NS2. They are not found, just like the group 1 elements, they are not found in nature as free elements. They are not found in nature as free elements. And are less reactive than group 1 elements. They also have a higher melting point than group 1 elements. Okay. Now, real quick, let's talk about some of the uh, properties, I guess, if you want to talk about hydrogen and helium. Hydrogen specifically. Let me recap this right here. Hydrogen and helium. Hydrogen has an NS1 configuration, an NS1 configuration, but does not share the same properties as the element in group 1. The properties of elements in group 1. And it doesn't really resemble them because once it's, for example, elements in group 1, they may have an empty 2s element so that they can, if they need to fill it out, usually in hydrogen, that's the most stable configuration. The same thing occurs with helium. Helium has an NS2 configuration. Um, it exhibits a noble gas nature because it is stable. Properties of a noble gas because of its chemical stability. But just kind of pointing those two out before we continue in the next video lesson, we'll probably talk about the P block elements and so on and so forth. I do want to, however, discuss real quick the sample problem that is on page 135. So let me go ahead and clear all these images. And then let's do that real quick. Now, in problem number, or sample problem A, it says, without looking at the periodic table, identify the group, period, and block in which the element that has the electron configuration of xenon 6x2. So xenon, which is the noble gas notation, 6s2. So what I want to know is the group, the period, and the block. So by looking at this, I can determine all that. So let's spotlight this real quick. So if I look at I know, for example, that the block, for example, it's a block S element, and the reason is, and I'm just going to abbreviate block. It's an S block because, you know what? Let me just do it this way. So I know that it is an S block, because of the sublevel. Secondly, elements of the S block have an electron configuration, or excuse me, pardon me. I know that the group is 2. And the reason I know that it is group 2, because I know that the electron configuration for group 2 elements is ns2. It's actually the exponent, in this case the 2, that indicates the group that it's in. So ns2, I know that it's in group 2 because this 2 right here indicates the group that it's in. I know that it's an S block, and also I know that the N in an electron configuration represents the period. So because there is a 6 in front of the S2, I know that this is a 6-period element. So again, I can determine the block because of the S. I know it's an S block. I know that is in group 2 because of the exponent here. And elements that are in group 2 have an electron configuration of ns2, meaning that the N represents the period. So because there's a 6 in front of this S2, I know that it is 6s2. Now, the second part of that problem wants us to find the electron configuration. Find the electron configuration. Find the electron configuration of a third period element of an element in group 1 and period 3. So we already, if you review what we discussed in the videos, we know that elements in group 1 have a configuration of N, S, 1, where the S indicates the block, which in this case is the S block. The S indicates the block, which is also an S block. And the 1 just indicates the group, which in this case is in group 1. And we already know that the N represents the period. So if we're talking about a third period element in group 1, We say that the n equals 3 because it's in the third period, and we know it's in the S block, and we know that it is S1. So what they want us to do now is to find the electron configuration. Basically, all of the elements, or all of the sublevels that go before it reaches 3s1. And we know this from what we did in the last chapter. So we always start at 1s1, or 1s2, excuse me, because they fit 2 electrons. Then we go to 2s2. Then we go to 2p6. And finally 2p6. And then, of course, 3s1. 3s1 is the highest energy level that is being, and it has only one electron. So 3s1. And once we found the electron configuration, they would like us to know if the group is more or less reactive. The element is more or less reactive than what we found here. So basically, we know that the xenon 6s2 element is in group 2 and the 3s1 element is in group 1. And we just talked about that, and we know that elements in group 1 are more reactive than elements in group 2. So we know that this element is more reactive. So, ladies and gentlemen, that is it for this video lesson, reactive. Hopefully I can write this legibly. The homework assignment has already been given to you in your platforms, in your LMS. And you, just in case you can't see it, you are going to answer problems 1 and 2 at the bottom of this sample problem. So stay safe, and we'll see each other in our next class. Bye.